Assalamu alaikum. Today I'll be demonstrating my project, which is a distributed brute force password cracker. Now I will be demonstrating it on the environment I have created, on a virtual environment I have created in my PC. Now, as it is a distributed system, so it is meant to operate in a distributed environment. But I have created, or should I say, I have emulated an environment where I have set up two virtual machines. Both are running Ubuntu 18.4 and they are on a same virtual network so they can communicate with each other. Now I will be demonstrating some of the connection parameters first. As we can see that there are two virtual machines running. So if I just could clear up and first I'll show the IP address of this one in settings, network settings. So the IP address of this machine, this machine is called distributed slave. So as this is a distributed environment, I have two identical virtual machines. One is named distributed and the other is named distributed slave. Now this is basically my cluster containing of two machines, which will be running my program. Now see, one device has an IP address of 192.168.1.15. So if I ping this device with my main distributed master device, so it should be able to ping it means that there is a connection. So as you can see, these are both connected through a virtual network, and both of the devices can communicate with each other. Now I should do the same with the slave machine settings network. Now my master machine has an IP address of 192.168.1.14. As you can probably see, they do exist on the same network. And they both in fact can communicate with each other through the network. So now that is established, one of the other things needed for setting up the distributed environment is that the both machines must be connected, must be able to connect with each another using SSH. So if I SSH slave 1, now I can use slave 1 machine for this machine as I have added it to the etc hosts file. Now if I SSH slave 1, as you can see, I have successfully managed to SSH into the other machine. Now I will exit from this. I will clear the screen. I have another terminal which is running the htop utility, which shows the resource consumption of a machine. I also have a terminal running htop here as well. Let me just go close this one. Now what I want to demonstrate here is, as soon as I run this command, now this command is actually executing my executable p2, which is the distributed brute force password cracker. Now as you can see, it is being executed via mpi exec. So in order to create it, I have used the mpi ch library. Mpi is a message passing interface. Now here I have given it 4 as the number of processes, and this is the machine file. Actually, let me just show you machine file. Machine file is the configuration file. Now as you can see here, the configuration files says that the slave 1 colon 2, it means that two processes will be scheduled on slave 1, and two processes will be scheduled on master. Now the machine file is a configuration file which tells MPI how many processes should be scheduled on each machine. Now P2 is my executable. Now this is some parameters that my executable requires, which are username and a hash file. And let me just get hash file here. Now this is the user dance, and this is its hash. Now it is hashed using SHA-512 crypt Unix standard. Now this application will actually be breaking off this hash, which is in the test file. Now let me just go ahead and execute it. Now as you can see, the program has initiated. Now I wanted to show you that as the program has executed, the resources on the slave machine have are being utilized up to 100%. So the CPU, this slave machine has only one CPU from the host operating system. So as you can see, its utilization is 100%. Now the stop on the master machine also shows that the CPUs are at their 100% utilization. Now I have allocated two CPUs for the master machine and only one CPU for the slave machine. So as you can see, as soon as the application terminates, both of the machines resources go back to normal as indicated by the stop. There are some errors with this virtual image. Now I did manage to get rid of that error. Now I have only used a password, very small password, only of 3 letters, because this environment is a very resource heavy environment, as it is running on a single computer, and my host computer's utilization is very high. So I only want to demonstrate this, and also that it would be able to crack this password within the time. Now I will be adding benchmarks with other strings of lengths and with more complex passwords. For now, I also wanted to demonstrate one other thing, and that is hashcat. I could not able to run hashcat on Linux because it uses OpenCL, and for some reason it was not recognizing any OpenCL device on this PC. But I do have integrated Intel GPU, sorry, this one, which is a OpenCL device. Now it is using OpenCL version 1.2. Let me just open the properties here. Now it will be more clear to you. As you can see, here it states that OpenCL version installed is 1.2. But when I installed Hashcat on Windows, now this is in Windows command prompt, I was able to get it running, and it was actually using GPU instead of CPU for cracking hashes. Now I'll be stating the benchmarks. I have used Hashcat as the main benchmark standard. Hashcat is a very advanced password cracking tool. It can utilize your graphics processor for cracking hashes. Uh, Now here I have a hash which Hashcat took almost 1.5 hour, actually more than 1.5 hour, as you can see the timestamps here, to crack this password, which was 5 character long. Now this was the password and this was the hash, and Hashcat managed to crack it in under 2 hours. Now I'll be adding these kinds of benchmarks in my report. For now, I just wanted to demonstrated how Hashcat works. And wait, let me just clear its port file. Hashcat saves the passwords it has cracked. As you can see, if I run this command here again, and now it says that all hashes found in port file. So it has a port file in which it saves its crack hashes. Let me just delete this one and try to run it again. Basically, this was the thing I wanted to show you. That Hashcat has managed to identify both of the computing devices available on this PC. And device one is actually the graphics processor, Intel HD graphics 4400 series, uh, and it is using device one as its main device. And device two it has identified is the Intel i5 processor. Now as it is working, as for status, it is actively working. You can see in task manager that CPU utilization is not as much as GPU utilization. So one good thing about Hashcat is it can manage to use GPU, and with it you can also use your computer for other stuff, as the CPU is nearly idle, uh, and it is primarily using GPU as its main compute engine. Now I'll just quit this. One other thing I wanted to show here is actually the comparison between GPU and CPU. Now with Hashcat and using GPU, Hashcat managed to crack this string, which was 5 letter long, in under 2 hours. Now the same string which I tried cracking with my own application, it took almost 11 hours to crack this 5 character long string. It was using only CPU. It was running only CPU, and it uses and I specified it to use 4 processes. Now, as you can see, it took almost 40,000 and 600 seconds, which roughly translates to 11 hours. Now, I had it running overnight. It took a lot of time, but in all fairness, Hashcat is a more advanced password cracking tool which is able to utilize OpenCL and graphic processing unit. So I did not run it just to benchmark with the Hashcat, but also with this command I have prepended perf stat, which gave me some statistics. Now the main statistics that I wanted was the cycle, instructions, branches, branch misses. Now these are the important hardware level events that I wanted to document, but because of the unsupported kernel, I don't know for whatever reason. Actually, the reason is, I think, because WSL is a relatively advanced technology, and perf has not updated itself to be compatible with this one. And perf does not actually uh, Perf does not actually work on complete virtual machines either. I have tried Perf here. Let me see if I have installed it here. So not on this virtual machine, maybe on some other virtual machine, but I have tried it and uh, it did not work. So some of the statistics that I did manage to get are these: the number of context switches, CPU migration, page faults. I'll be writing in detail about them in my report, and I am still trying to get the Intel VTune working. But what I did manage to get was that the well grinds tool, cache grind, I did manage to get it working, which is a good tool for seeing the cache performance. Now I have run this program. This program actually encrypts the argument given to it. Uh, the program is E and this is the argument, and these are some cache statistics. Now these are instructions, I for instruction and D for data, references and misses. I'll be going over in detail in this tutorial about these statistics. Now I want to go over the cache grind utility from Valgrind. So a cache grind tool within the Valgrind package provides us with statistics like this. Now these are basically uh, cache references, cache misses, and cache hits at different levels of cache. So these metrics are related to the cache references that the application makes. Now I'll go in detail about these. Now first of all, I here refers to the instructions, and refers mean references. So the total instruction references made is this amount, and I1 means that at level 1 cache the misses were this much, and at LLI means the misses at level 2 cache. Now the misses at level 2 cache, the instruction misses to be specific are this much, and these metrics show the miss rates at level 1 and level 2. Now the reference means the data references, and data references are in two columns. Here it means read and write. So the total data references made, the D1 means the data references made to L1 cache, and these are the misses, the read misses and write misses. LLD means at level 2 cache data misses, and again these are the rates for both read misses and write misses at both L1 and L2. Now LL here refers to last level. Now I have looked up the documentation, and it says that LLL is usually for the last level. Means if your computer has two levels of cache, then it will basically refer to L2. But if your computer has three levels of cache, then it will refer to L3. So in my case, I have three levels of cache. As I can show you with CPU-Z application. Now these references are these are the amount of references made to the level 3 cache, and such as and exactly as before, this the amount of misses, and again for both read and writes. So L3 cache is a shared cache. So it refers to the board types of references, data and instructions. So here we can see the amount of read references and write references, and subsequently the misses and miss rate. Now if I can just open this, and here in the caches tab, you can see that there are three levels of cache in this PC. Now with this, another thing I wanted to show you is that the cache grind also creates this report file, uh, which is by default named as cache grind.out. The process ID. This is actually the process ID uh, of the process through which the cache grind run. So these can be very useful. This is a function and that can be used to open these files. Now if I just specify file, now here's a lot of useful information that one can use. So here, as you can see, a summary of caches. Now I want level 1 cache, and it says this much capacity of that cache, and it is 8-way associative, and 64, I guess it means bytes. 64 byte could be bandwidth. I might have to look it up. Oh, and it says it is 8-way associative, and D1 data at level 1 cache also 8-way associative, and LL cache means the last level. In this case, level 3 cache is 12-way associative. This can be also verified through this application. As you can see, 64 byte line size. So this is what the 64 is referring to. So 8-way set associative, 8-way set associative, and at level 3 it is 12-way set associative. So now we'll see what uh, other information that it provides us. So basically, there are like 12 columns, and here at the end it says file functions. So I have opened up the cache grind documentation, and I will just walk you through this CG annotate and what this file is actually showing. So the metrics in the file are mentioned here. So I cache reads. So instruction cache reads, that is instructions executed, and I guess that the instruction is executed for the program. And I1MR here, it means that I1 level 1 cache read misses. So if we could, as we can see here, there is in fact a column of I1MR. So the level 1 cache instruction miss rate. Uh, so basically, this file can show the exact function, and the function and the relevant statistics, cache statistics, such as I1MR instruction 1 cache miss. So basically, for a large program, optimizations can be made to each individual function in such a way that they make less misses, cache misses, or they are more aware of the cache. So for this purpose, it is a very neat utility. And now we'll just move on to the other matrices. So I2MR, so level 2 L2 cache instruction read misses, and so on and so forth. DR for D cache, data cache reads, that is memory reads, and D1 cache read misses for data at level 1 cache misses, I suppose, and L2 cache read data misses. L2 cache, this is the metric for data misses at data read misses for L2 cache. And as we have seen before, for data misses, there are two type of misses, read misses and write misses. So it here specifies exactly what kind of miss. And decache writes, write memory writes. DW specifying D cache writes, and D1 MR, D1 cache write misses, and D2 MR data write misses at level 2 cache. So this can be used to optimize optimize the program at function level. So I was going through this file, and I saw that basically most of these functions or about 85% of these functions, the function which says Perl construct and Perl save sys malloc. So these are all related to the cryptographic function I have used in the program, that is script, and it is all related to the main header file that function uses, the main libraries that script function uses. And there are some other Linux specific header files that are also referenced here, uh, or C compiler specific files such as malloc.c are specific here. So basically, for a function or for an application which requires a high level of optimization, this utility can be used to point out the functions which are not very cache friendly, should I say, and it is a very useful utility for making the application responds more to the way that your computer's cache works. In order to get the results from perf, I had to install Ubuntu natively on a device. So I found out that the virtualization environment kind of blocks the perf utility to get the hardware performance measures. So in order to get them, I had to install a completely new operating system. In this case, it's Linux based Ubuntu 20.04 long-term support. So I have set up everything required to run the program here. As you can see, I have typed out the command and the exact command. Uh, in a similar environment, I have installed GCC and MPI, and also perf. I I would like to show you how the perf lists in how the perf lists its supported events now. So if I run the command perf list, you can see that I can get all the kernel PMU events. Now these are the compute units within the processor which allows perf to record the counters, values of counters. So you can see here now I have supported branch instructions, branch misses, and CPU cycles and everything, and all the hardware counters that were missing from the Windows environment. Okay, now I had to confirm that it is still recording. Okay, now first let me just set a little thing. Okay, now I want to set actually what I am doing is I am going to set the password within the test file that I will attempt to break with this application. Now if I just run this, I have written a small program which encrypts the argument I gave it. So if I run this, it encrypts it with a SHA-512 crypt Unix standard. Now I will use this in the test file. So this is the test file named test, and I'm going to paste it here. I'm using the Vim editor, and by the user dance I am going to paste it here. So I had to make the password short, so that uh, it is that the application breaks it during this video. So now as I have done that change, I will just save it, and now I will run this command. So sudo for root privileges perf stat for statistics regarding the execution of the following command. So here the same MPI exec MPI for message passing interface for a distributed environment, and I have specified cores four processes, and this is my application and the arguments required by it. Also I want to open htop here, which is it's always nice to see your program's resource utilization. So here this machine has two cores, and they're about running at half of their efficiency. Now I will run this command, and here goes, it's asking for my password. Okay, now there's been a mistake. As you can see, it did not detect salt, so it may be because of extra space. So let me just look up the test file. Oh, here it's supposed to be there's supposed to be a dollar sign here, because this is the format of the SHA-512 hash. Now I will just save it, and I will run this again. Now it has properly detected salt and hash. Now it's attempting to break it, and let's look up the resource utilization. You can see both of the processors are now at 100%. So it means that this application is running and attempting to break that password. So I will just let it run. It will probably take a few seconds. So as it is attempting, oh, it's done. So as you can see, and the password I specified uh, was trf. So this application, the application within the application, the process which got the range between O and U found this password, and it took it took this application about 22 seconds, sorry. And now the main perf summary. So as you can see, now the previously unsupported events are now listed here. Now starting off with the first one, the task log. The task log is actually the sampling clock, which is task specific for. So for this task, uh, this this should be the sampling time. And sampling time for these hardware for the following hardware counters. So now the next metric is context switches. I have already talked a little bit about these software events. So this is basically the software related event. This is basically the amount of time the OS, the host OS switched the processing time from this application and gave it to some other application. So these are basically context switches. There were about 23,900 context switches during the application, during the execution of this application. And CPU migrations, I am not really sure about the CPU migrations. I will have to look it up. And But it is not as relevant as some of the hardware events like cycle installed cycles and branches and branch misses. So next is page faults. Page faults is the virtual memory misses for operating system. So it had this many page faults during the execution. Now the cycles. So the cycles basically tell the number of CPU cycles that were consumed during the execution of this program. So there were this many cycles. And installed front end, installed back end cycles. So these are the pipeline stalls that occurred during the execution. And you can see it provides us with an crucial statistic, that is stalls stalled cycles per instruction. And there were 0.05 stalls cycles per instruction. For each instruction there were about 0.05 stalls. And now the instructions, these are the total number of instructions executed. And this is my year IPC, that is instruction per cycle. So there were about 2.56 instructions executed per cycle. And now branches, these are the total number of branches, and these are the branch misses. Uh, so from total branches, these were the branches that were missed, or mm, that were uh, mispredicted. So this is the rate of mispredictions or branch misses. 0.62% of the branches out of all branches were missed. So for our applications total time, it was 21 or around 22 cycles. And with the overhead of perf, it took about 55 seconds to elapse. uh, for now, this will be all. I will be registering and reporting all these measures for different execution runs in my report. Thank you. Now I will be showing the results of the VTune profiler when profiled on Hashcat. So I finally managed to get it working. The main reason was actually quite simple, and VTune profiler was limited by the OS because of its virtualization capabilities. So if anyone does have that error, all you have to do is go to this Windows features menu, and you have to disable the virtual machine platform and Windows hypervisor platform, because that limits some applications capability to communicate with the hardware. Finally, I want to talk about the statistics that were produced by the Intel VTune profiler. Now, these are the Hashcat's execution analysis. Uh, so basically, this is a very detailed summary of the run, and there is some graphical representation, and some of the issues, just as it says here, were uh, recorded and reported. And now I'll be going over some of the main metrics here, like these clock ticks. These are the clock pulses, and the clock pulses that were consumed during the execution. And next up is instructions retired. So this means that the total amount of instructions that were exited the pipeline. Uh, and Here it shows the actual number of instructions and also the actual number of clock pulses. Next is CPI rate. CPI is which is clocks per instruction. So this was the CPI rate. 1.256 was the CPI rate. And next we have also uh, metrics stats like bad speculation. So this is a great stat measure for optimization from the perspective of optimization. So bad speculation has branch mispredicts. So here it says the percent of branches that were mispredicted. um, in order to have a good understanding and make your application more optimized to certain workloads, these statistics can be very helpful. And also, I see here I cache misses, which is instruction cache misses. It is front end latency, so I think that is at level 1. It should probably on level 1. The I cache misses for instruction references. Next, down here, I found another great metric, which are this ALU operations utilization. So these port 0, port 1, port 5, port 6 are actually the functional units to which this percent of the workflow was and divided. And the ALU operations, like it says here, ALU operations were divided by this percent to these respective functional units. Uh, same as uh, Same as for load operations utilization and store operations utilization. So for ALU operations, it says to ports from port 0 to port 6. So I guess there may be around 7 functional units for ALU operations. I am not really sure about it, but this could be it. But for the execution of this program, 4 functional units were used, and and the work was distributed. The ALU operations were distributed among these 4 functional units. And at last, it says the average CPU frequency, which is the base frequency of the processor, and total thread counts, the total threads that were spun up for this application. So, I- Intel VTune Profiler is actually a very detailed profiler, and it provided with very good matrices. And here also I see LLC miss, just like in the well-grinds cache grind utility. It also mentions the LLC misses, which is last level misses. And here we can see that a little pop up appears, which is actually telling the details about this metric. So the last level cache is the last and longest latency level in the memory. So it is most probably will be in the level third cache. And I also have some other tabs here, and basically what these tabs told were the thread level, matrix for this program. So as you can see, threads along with this IDs, and we can see the utilization of each thread. And just by looking at it, it seems like much of the threads were idle most of the time. And here we can see that clock ticks and instructions retired CPI rate are listed by exact functions, uh, and this is pretty much it. And VTune profiler has helped a lot in order to understand the hardware level performance counters. So this will be it. Thank